Okay, so when you think about an electric motorcycle, what's the first thing that comes to mind? Probably the battery, right? Or maybe that big electric motor. But today, we're going to dive into something you can't see, the bike's brain. It's this incredibly complex network of control systems that acts as a nervous system, dictating every single move the bike makes.
It really is a unique feeling, isn't it? That silent, seamless, almost magical rush of power. But have you ever stopped to wonder how that actually happens? How does a simple little twist of your wrist translate into such precise, instant power? Well, that's the magic we're going to unpack right now, looking at the incredible dance between hardware and software at the heart of the machine. All right, so let's start at the top with the hardware. This is the core architecture, the command center for the entire motorcycle. Think of this stuff as the actual physical organs that make up the bike's electronic brain.
So, running the whole show, you've got the Vehicle Control Unit, or VCU. This is the Master Coordinator, the CEO. It takes in all the information, your throttle input, your speed, sensor data, and makes the big picture decisions for what the rest of the system needs to do. It is literally the brain of the operation.
Okay, so if the VCU is the brain giving the orders, the motor controller is the part of the nervous system that controls the muscles. It gets these low-voltage commands from the VCU, and using these incredibly powerful and fast electronic switches called MOSFETs, it chops up the raw, high-amperage current from the battery and feeds it to the motor with absolute precision. And of course, you can't forget the guardian of the power source, the battery management system, or BMS. Its one and only job is to be the battery's bodyguard. It's constantly watching the voltage, the current, the temperature, making sure the most expensive and vital component on the bike stays safe, healthy, and efficient. So let's put it all together. What happens in that split second when you decide to go? Well, you twist the throttle. The VCU instantly sees that request for power. It zaps a command over to the motor controller using something called a CAN bus, which is like a high-speed internal internet for the bike. The controller then serves up the exact amount of power the motor needs, and all the while, the BMS is watching the battery to make sure it's handling the load. And all of this happens in milliseconds. It's incredible. All right, so we've got the hardware down, but what makes it all work together so beautifully? That's where the software comes in. We're talking about the sophisticated algorithms that are really the language of motion that lets the controller speak to the motor with such finesse. You know, at a really basic level, the difference in how these motors are controlled comes down to the shape of the electrical wave the controller sends. A trapezoidal wave is kind of blocky, like a series of on-off steps. It gets the job done, but it can be a bit jerky and you can often hear it buzzing. A sinusoidal wave, on the other hand, is a perfect smooth curve, and that smoothness translates directly into quiet, refined, and efficient power.
And you can really see the difference this makes to the rider right here. Trapezoidal is fine, it works. But the real game changer, the gold standard, is field-oriented control, or FOC. Think of FOC as a super smart version of sinusoidal control. It's not just sending a smooth wave, it's constantly tracking the motor's exact position to time that wave perfectly. That's what gives you that incredibly precise, almost telepathic connection between your wrist and the wheel.
So you see, it's not just about getting the wheel to turn. These control systems are doing so much more. They're actively managing energy and shaping the entire dynamic personality of the bike. This is where the engineering really becomes an art form. A perfect example of this is throttle mapping. This is all software. Engineers can literally write different personalities for the bike. In eco mode, a half twist of the throttle might give you some gentle, easygoing power. But switch it to sport mode, and that same half twist could unleash a tidal wave of torque. It means the exact same bike can be a tame commuter 1 minute and an absolute beast the next. So, you ever wonder how some electric bikes can hit those crazy high speeds? A lot of the time, the secret is a clever trick called flux weakening. The best way to think about it is like this. The controller smartly manipulates the magnetic fields inside the motor, which lets it spin way faster than it normally could. It's kind of like giving the motor an electronic overdrive gear for the highway. And then there's regenerative braking, which is it's such an elegant piece of engineering. When you slow down, the controller tells the motor to act like a generator. It takes your forward momentum, your kinetic energy, and turns it back into electricity to feed the battery. Not only does this give you a little extra range, but as a bonus, it gives you that familiar engine braking feel you're used to from a gas bike. Okay, last but definitely not least, let's talk about the safety systems, the guardian angels that are always working behind the scenes. These systems are absolutely non-negotiable for protecting you, the rider, and all of that sophisticated hardware. All right, picture this. You're out on a beautiful, winding road, it's a hot day, and you're really pushing the bike. All that performance is creating a ton of heat in the motor and the controller. The system is starting to get stressed.
What happens next is something called thermal rollback. Before anything gets hot enough to cause damage, the controller starts to intelligently and smoothly dial back the power. Now, this is super important. This is not a failure. It's the opposite. It's the system being smart, protecting itself from heat damage so you can live to ride another day.
Okay, how about another one? A situation every rider dreads. You're pulling away from a light, the pavement's a little slick, and you give it a bit too much throttle. With all that instant electric torque, the rear tire can break loose in a heartbeat.
And that is where traction control is an absolute lifesaver. Sensors are watching the speed of both wheels hundreds of times a second. The instant it detects the rear wheel spinning faster than the front, it cuts the motor's torque just enough to let the tire regain its grip. It's an incredible safety net.
And let's end with a super simple one, but something I'm sure we've all done or almost done at some point. You hop on the bike, you're all set to go, but you totally forgot to kick up the side stand. Enter the kickstand cutoff switch. It's so simple, it's brilliant. There's a little switch that tells the VCU whether the stand is up or down. If it's down, the system simply refuses to engage the motor. No power, nothing. This one little feature has probably saved millions of riders from that embarrassing slow-motion tip-over in a parking lot. So what's the big takeaway here? At the end of the day, an electric motorcycle is this tightly woven fusion of hardware and software. The hardware, the controller, the VCU, gives the bike its potential, but it's the software, the algorithms, that truly defines its performance, gives it a personality, and most importantly, keeps the rider safe. Which brings us to a really interesting thought to end on. We're in an era where a bike's entire character can be changed with a software update. So does that mean the future of motorcycling, the future of what it feels like to ride, is going to be built by engineers in a workshop or by programmers on a laptop? It's definitely something to think about.